Welcome to Unit 1, Lesson 5. In this unit lesson, we are going to talk about overflow and rounding. For our warm-up, I want you to imagine you work at a local store. In the register, all you have are 9 $10 bills, 9 $1 bills, and 9 dimes. So I want you to think, what's the largest amount of change that you can give someone? What's the least amount of change that you can give someone? And what would you do if someone needed 7 cents in change? So I'm going to put a timer on the screen and give you some time to answer that in your journal. Today we're going to explore what happens when you don't have the right places to store information. This can happen when you try to store very large numbers, very small ones, and pretty much everything in between. The goal of this journal prompt was to understand the very real problem of making sure that enough place values are available to represent numbers. So the largest amount of change that you would be able to give somebody is $99.90. The least amount of change you would be able to give somebody is 10 cents, and you can't give somebody 7 cents. You also can't give someone $1.25 in change because you have no nickels. So at both extremes of the number range, large and small, and in between numbers, you are unable to build some numbers because you don't have the place values to do so. So, we will start exploring large place values to see what happens when a big number gets too big. I want you to go to the binary odometer widget on level 1, and that is going to be this page. This is a widget that simulates a car odometer, a device that tracks how far the car has driven in miles or kilometers. And I want you to explore the odometer to understand how it works. I'm going to give you some time to explore. And when the timer runs down, then we're going to move on to the activity. Now I'm going to give you a challenge to tackle with the binary odometer. I want you to write your response in your journals. I want you to set the binary odometer to the highest number possible and then let it run. Okay, this is the highest number possible. So I want you to let it run, and I want you to write this response in your journal. What happens to the odometer reading when it runs? Does the odometer still show the distance driven by the car? Take a couple of minutes and write that response in your journal. So I have set my binary odometer to the highest number that it can go because it's either ones or zeros. And that's this value right here. So whenever I hit start, what happens? Okay, all of those ones turned right back to what? Let's go back. Okay, I'm going to slow it down. Look at that. It goes from maximum all the way back to all zeros. Okay, now if there were a place value here, that number would have turned to a 1. But as you can see, all the numbers should flip to 0, and the one to the left should flip to 1. But there's not anything else to the left. We're out of place values, so the numbers flip to 0, but nothing flips to 1. The number we are trying to represent does not fit in the number of bits we have available to accurately display it. Like a bathtub that has reached its maximum capacity for holding water, it is now overflowing. The odometer has reached its maximum capacity and has reached overflow. So what I want you to do is I want you to take a moment and I want you to complete the check for understanding. So bubble number 2, and you can do that by clicking continue, please. And then I'm going to give you a few minutes to do that. And then we're going to look at the limits of our flippy-do. Okay, so grab your flippy-do. And we're going to look at the limits of our flippy-do. When we're looking at our flippy-do, how many place values do we have here? 1, 2, 3, 4, 5, 6, 7, 8. What value would cause our flippy-do to overflow? Meaning all of these bottom numbers are set to 1. What value, what is that value? And what value comes after that would cause it to overflow? What adaptation could you make to the flippy-do to represent that value so that way it doesn't overflow? Using your newly adapted flippy-do, how many total numbers can be represented? Okay, I'm going to put a timer on the screen and give you some time to answer that. You're going to answer these 3 questions in your journal. So I'm going to put a timer on the screen to allow you the time to do that. Now that you have started thinking about place value and overflow, we are going to work on a different problem. Okay, what happens when there aren't enough place values to represent a number? Let's look at this candy shop challenge. So if we were in class and doing this in class, you would have a partner. If you have a partner that you can work with, that's great. If you don't, I'm sorry. I would maybe try to find somebody that you could work with, or just tackle this on your own, because you are more than capable of doing that. Okay, so let's look at the candy shop challenge. You are opening a candy shop. Here are the prices of 4 candies that you're going to be selling. These are the candies. Okay. You need to put a binary number into your shop's computer system to represent the price for each candy. Your computer system takes input in 4-bit binary digits. So, to do this activity, come up with your representation for each of these values using your flippy-do. So ideally, whenever you get done with this, you would discuss with your partner, how did you go about deciding which binary number to use for each piece? And in your system, who pays the difference between the true price and the value stored in your computer system, the shop owner or the customer? So those are just some questions that you can answer in your journal also. Even if you do have a partner, write down what you would say for these answers. We would typically discuss these in class though. So the flippy-do doesn't have the precision needed to represent these fractional values, and in that case, decisions must be made on how to represent those values. In this case, those decisions impact who ends up benefiting when it comes to the price of each candy. So here's my next question. These scales are from 2 different manufacturers in the stores. Okay, they both use 4-bit binary numbers to store and display the weight of candy. The bowls of gummy bears each weigh 3.3 pounds. Okay, so this scale right here always rounds the weight down to the next whole number. And if you use your flippy-do, you'll see what that whole number is. Okay, 0011. That's 3. So if you round 3.3 down, you get 3, right? This scale over here rounds it up to 0100. So from 3.3, it rounds it up to 4. So here's a question, and write this in your journal. What problems could come from having both of these 2 types of scales in a single one of your stores? I'm going to give you a moment to answer that question. To end our lesson, the most important takeaway is to understand that bits can represent a limited amount of information. Okay? Here's a couple of questions, or a couple of points first. Binary can precisely represent some fractional amounts from the decimal number system. Okay? So 4.75 in decimal would be 0.100.110 in binary. And this is what that looks like. Okay, our flippy-do only goes, like, this is the only part of the flippy-do that we use, but you could go even smaller. Okay. The second point, binary cannot precisely represent other fractional values from the decimal number system, and an example of that is 0.39. So in your journal, answer this, and you can include that this is the wrap-up for Lesson 5. What does the binary odometer show about representing large numbers? If we had a big enough odometer or flippy-do, could we possibly represent every single number, every possible number? Answer those questions in your journal, okay? Then I want you to go to Unit 1, Lesson 5, and answer Bubble 3. Answer those questions. Let's add the following word into our journal. We've got a vocabulary page within your journal. We're not going to use the digital template, so start with the words. your initial definition and a visual representation of the word. So our word is going to be overflow error. What is your initial definition of overflow error? And then what is a visual representation of an overflow error? And then we will go over some of our journal responses in class.